So here we are talking about Monte Carlo path tracing, and also like how to generate photorealistic images with GitHub CoPilot. So that's a kind of really fancy name, but we'll dig into each part. What is about, like what is Monte Carlo, what is path tracing, what is GitHub CoPilot, and how all these tools will help us to generate photorealistic images. So it will maybe be a lot to digest in like 45 minutes, but I built the slides so you can refer to them later if you want to try it by yourself. And like every part will be independent, so it's not a problem at all if you miss a point. Talking about myself, so I'm Loic. I'm working at Cunningham QuadrPad. So we are building a screening and live interview product to help companies to improve their hiring process, and help them basically find candidates based on their skills rather than their resume. So myself, related to this topic, I have implementing several ray tracer, path tracer in my life, mostly during my education in C, C++, Python, JavaScript. And why? Because like I strongly believe path tracing and ray tracing in general is a great way to learn some core programming principles. And it is very exciting because you have like a visual rendering of what you're building and your algorithm. So I will try today to share this enthusiasm and passion about this topic, and hopefully give you also the desire to implement one on your own. So first, talking about path tracing. So what is path tracing? So path tracing is a subset of what we also call ray tracing. So the idea is to generate photorealistic images. And by photorealistic, I mean also we will try not to break the law of physics and the physics of light itself to generate these images. So of course we will compromise and try to like get closer to this realistic rendering compared to like other techniques that are not taking in consideration the law of physics, but just like try to generate an image that is as close as possible to the reality. So how we will do that? So basically we will just have a camera, have a scene that will be like a 3D scene with basically triangles or objects inside it. We will also have light sources, and we will try to simulate how the light interact with objects and with our camera. So why this is called path tracing or ray tracing? Because we will basically shoot rays from the camera toward the scene to try to like intersect objects inside the scene and simulate the light. And the idea is to get as close as possible to these images, so like photorealistic images, and we will see in detail how. So basically, as I said, we start from the camera, from your eyes, we shoot a ray, we try to intersect object, and we try to simulate from this object the direction and the path of the ray. So sometimes the ray will like bounce and go to another object. Sometimes it will go through the object because there is like some transparency in this object. And we also like try to do this recursively, trying to like reach out to the light and compute the global lighting of the scene. So it's like a recursive, and it will go in depth inside each ray to make sure like simulate the bouncing and all the different lights for an object. So this is not to know, of course, something nice you can put on a shirt to sound cool with other computer graphics engineers. So basically, this is what we call the rendering equation. And this is what we will try to emulate, at least get as close as possible to. So this basically says that for a given point in space, the lighting here corresponds to on the light that is coming from all the direction. So it means through an object, if it is transparent, for example, but also like direct lighting from a light, or the light bouncing from another object to it. So all the light coming from all the directions. But of course, this is impossible to simulate if you want like to take into account everything, and also because this is almost continuous. So we will try to approximate as much as possible and as close as possible to this behavior. So take into account the light that is coming from every direction in a specific point of space. So to emulate this, we will use a method called Monte Carlo that is used in a lot of different topics. It uses basically the power of randomness to average a result. So this is an example of Monte Carlo to average pi, the number of pi. So basically what we do here is we generate random points into a 1 by 1 square. And if the distance of to the origin, the 0, 0 point, is less than 1, we consider it's in the circle. And by computing the ratio of the points that are in the circle versus the points that are out of the circle, we can approximate pi. Because in average, randomness gives us a result that is close that we expect. So because it's here impossible to compute the light that are coming from all the direction, what we will do, we will generate random rays that are randomly going to any direction. And if we are doing this enough time, in average, this will give us a result that is close to the reality. So is there a lot of math physics required? Yes. So there is multiple solutions here we can do. We can like read papers and understand equation on Monte Carlo path tracing. This sounds boring. We can dig up on like a big book on path tracing. Also like 2EV. We can also like retrieve some amazing courses by some amazing teachers, but we are not student anymore. So instead of that, what we will do is just use our tab key. Because there is an amazing tool called GitHub CoPilot, which is an enhanced autocompletion inside your IDE, which is for real this time AI based. It takes into account all the public code and text in the internet, and thanks to an OpenAI model based on GPT-3, try to give you very advanced autocompletion. And so we will try to get rid of all the mathematical and physics law and very hard computation to do, and trust Copilot to generate code and functions for us. So let's roll. Let's get into it with all this like basis and try to build the first realistic photorealistic image generator using GitHub Copilot. So here is just like basic index.html. I just inserted a canvas here to render the image and the button to render the image, very basic. So first magic using Copilot. I just want for when someone click the render button to execute a function. So I just like put my cursor and everything was proper here. So the click function. And you can see here also that between the first example and the third one, he was proposing me to use jQuery, but I just like renaming to use document get element by ID. And it already learned from that. And the next time he proposed me a completion, it was with get element by ID. So it's not only about completion, but it's also taking into account like the coding style I use. And as you see, I also choose like JavaScript and very basic JavaScript, no library, nothing, just to like make its life easier. And also like this function, update canvas pixel, just like to print a pixel on a screen, everything is generated. So this is something you could have done using Stack Overflow, but here directly inside the IDE, and just use the tab function. Okay, next one, I want like to try my code just to iterate. So I threw all the pixel on the canvas and just like show a black pixel. I just typed the for and all the condition, all the for loops and the update, calling my previous function with the right parameter in the right order, the right name. So this is already pretty amazing, but still a black square. So now what we need is a scene to render. A scene composed of different objects and lights. There is one nice scene you can find on the internet, which is called the Cornell box. It is very famous in ray tracing because what the user, the searcher did here is they build the scene in real, take photo with a real camera to compare the results to the photorealistic renderings. So here is an example. So on the left, this is a real camera in real life, the real scene. And on the right, it's a simulation, photorealistic using path tracing. So you can see both are very, very close to each other. And so all the like triangles, all the description of the scene is available online. So it's a good tool to start with to compare your results to other results of other people on the internet. So I just defined the scene. So your CoPilot, sorry, didn't help us, of course. So I just defined a scene. It's just a JavaScript object with objects and lights. The camera also, taking the parameters of the Cornell box. So nothing fancy here. Defining different type of objects inside this scene. So I've chosen to only use a sphere and multiple triangles. So a sphere, it's only described by its origin and a radius and a color. And a triangle is defined by its 3 vertices. And there is a light too with a position and a color. So very, very straightforward. And so we are starting to use the power of CoPilot to just give us some very basic functions, tools that will be referenced by other functions later. Of course, I could have started by just defining other function and then defining this one if I need. But I know that I will need this one, so let's define them. And also because this will impose to CoPilot a style, a coding style. So we will be able to see in the future if CoPilot is able to follow this coding style. So I'm just defining some very basic vector function. Of course, CoPilot is just like generating all the function just based on the name. Like all vector function, dot products, cross product, everything is generated by CoPilot. I just have to type the function name. Very useful. I can also like just type a comment actually before the function, and the function will be generated too. Also RGB2X. So I'm kind of forcing my way to represent colors. I will represent colors by RGB, red, green, blue. But to draw to a canvas, I need hexadecimal color. So this is a function. Also like very, very complex, but CoPilot did it for me. Nice. So now let's get into the image generation itself. So as I said, I will like shoot rays from the camera and try to intersect objects in the scene. So the first iteration will simply be iterate through all the pixels of the canvas, generate rays from this pixel as it was coming from the camera, and try to intersect object. And if I intersect with an object, I will just take the color of the object and show it to the canvas. So I should have a very flat view of the scene with only the object's color in it. So let's get into it. So basically, step 1, for each pixel, I will generate a ray from the camera, depending on the pixel position of the screen, obviously. I will iterate through all the objects of the scene, try to find if there is an intersection between this ray and the object on the scene. If I don't hit any object, I will just return black from like the void. And if I have one of multiple hit, I will take the nearest object from the screen and return the object color. So there is like, this is a 2D intersection between a ray and a sphere. In 3D, it's kind of complex, so I don't want to get into like the mathematical detail of it. Same for triangle. It's not that easy to intersect a ray with a triangle. So let's ask again CoPilot. So first thing, shoot a ray from the camera. So this part actually is very tricky, and CoPilot failed. Why? Because there is a lot of different ways to shoot ray from a camera because there is a lot of different type of camera. There is a lot of different way to represent a camera. So here, it's basically failed to have my context, I have my way of defining a camera and generate a function that matches my style. So I had basically to fix it myself for the first time here. And it is actually pretty straightforward, but let's not get into the detail. So basically generating a ray from the camera. Next thing is like the main function, so path trace. Here, I just typed the name of the function and it proposed me something. So it proposed me to find the intersection using a scene, array, and some depth. And if there is an intersection, just return the color of this intersection. So this is actually pretty good. There is this like depth parameter, which is useless for now, but will be useful later. And also like this intersection, like it's kind of strange to put a function here to get the color. I could have the color inside the intersection itself, but okay, for now, I think it will be good enough for us. So now we need to actually intersect object. So first, I just typed the find intersection function. And it was proposing me the wrong parameters because I don't want to have like array and objects. I want to have the full scene and array. So I just typed the parameters I wanted and it just like changed and proposed me the good thing. So what he's doing here is just like iterating through all the objects of the scene. For each object, find the intersection for this object. And if the intersection is closest at the previous one we find, it's becoming the closest one and returning the closest one. So this is actually pretty good. The only bad thing is that by default, it is initiating distance to infinity. So if I don't have an intersection, I would rather like to return null rather than an intersection with a distance of infinity. But this is pretty good. So let's go further with it. We need to like define this find intersection for object functions that don't exist yet. So I'm just typing again the name and it generates the function. And you can see here that it is actually pretty good to interfere the context because it knows that I have only defined two types of objects that are sphere and triangle. So it proposed me a switch with only sphere and triangles and the correct function name for both of them. So this is pretty amazing. So going further, defining intersection for sphere and triangle, again, mind-blowing, just typing the function name. And you can see like this is kind of math heavy. There is a lot of things going on here. But basically, it is all right. I have an intersection between a ray and a sphere, and it's returning me the point of the intersection and the normal, which is like the vector at the point of the intersection. So this is actually pretty good. I'm just missing some properties that will be useful later that I will add myself, which is like the object itself, the sphere. It's useful to have it in the intersection. And also the distance. So I will put directly the distance into that object. So here at that time, I've updated the code to add the objects and the distance. And guess what? For the next one, mind-blowing again, the all function is generated and it already learned that I need the normal, the object, and the distance into the returning object. So this is really amazing. I don't have to update it again, and everything looks perfect. So next, I'm using like my tab key more than the other key for now. So this is the main function we wrote it before. I just need now to, instead of just putting black for every pixel, shoot a ray from the camera. So I'm just like calling the function. So again, CoPilot just proposed me. He made some little mistake, but that's all right. And basically it was on me. Like he assumed the camera was in the scene, but I defined the camera outside of the scene. But actually, I think that's on me. It could have been nice to have the camera on the scene too. And also the ratio, it replaced the ratio of the camera by the canvas width divided by the canvas height. which is actually also like better than defining the ratio inside the camera. So you made mistake, but I think maybe that was on me. So next one, just like getting the color from this ray. So I'm just like path tracing the ray I generated from the camera and shoot it to the scene to get the color. And then using my RGB2X, and again, CoPilot just like proposed me this function by default, turning the color into hexadecimal. And that's it. So you can see like I've not written that much code to get to that point. CoPilot did a lot of the work for me. And now I have a scene, which is like the Cornell box with red wall on the left, green wall on the right, and the sphere inside it. So very flat, just like intersection with the object, but it's a good starting point. So now I have talked also about Monte Carlo. So let's see the first Monte Carlo example for anti-aliasing. So you may not have noticed, but if I zoom in, you can see like the red wall is aliased a little bit, because sometimes, if I'm not lucky, some pixel will be like white, hitting the white wall, sorry, and the next one will be red, hitting the red wall. Ideally, what I would like to have is, when this happens, having some pixels here that are between red and white. So how to do that? Again, use the poorness of random. So for each pixel, instead of just shooting like 0, 0, 0, 1, 0, 2, I will generate for each pixel a random number of points. So every time I will like shoot a ray from the camera, I will not take the exact like 0, 0 coordinate, but I will generate around that a little bit of randomness, as you can see here. But to do that, we also need to add n pass per pixel. So instead of just shooting for each pixel one ray, I will need to shoot multiple rays and average the results. So like as with any Monte Carlo method, in average, it will return me something close to the real results. It will return me actually something close, like if I would iterate through all the possible sub-pixel of a pixel, which is like not impossible to do in real life. So that's great. So let's do that. So again, CoPilot is helping us a little bit here. So I'm just adding another for loop to iterate not only one time, but n time, first per pixel time for every pixel. I'm randomizing the coordinates of the pixel. So again, just adding math random here, math random here. It makes like between 0 and 1. So every pixel is sampled inside. And you can see like if I'm doing only one pass, this will look like that, very noisy. Because again, like random is also a matter of luck. So that's why I need to do it a lot of time, like 100 times, 100 pass per pixel, and average the result to make sure to get something smooth rather than something very noisy. So let's do that. And again, trusting CoPilot. So I'm just generating a pixel map. So I want to like store for each pixel, every time I generate a new pass, the aggregation of all the values, so I can average all the pixel at the end. So I'm just trusting CoPilot here with the type. So I'm just generating an array of like canvas width times canvas height to make sure to start that. Trusting CoPilot here. It made a little mistake because it called the function add vectors, but it is about colors. So I just switch and add another function, add colors, and it helped me to build that function. So just basically adding colors. And at the end, when I have like did my path, I just need to divide the color of each pixel by the number of paths I did. Again, small mistakes, divide vector instead of divide color, but that's fine, that's okay. And that's a result. So pretty smooth, anti-aliased. And this is one of the techniques we will use a lot, the randomness, because now that we have the framework, we will shoot a lot of paths per pixel. So every time we want to iterate through something, instead of iterating through all the possibilities, which is like not doable, I will just choose one randomly, and in average, this will give me the results I want. So now, let there be light. So have you seen the scene is pretty like flat? So we need to add light to it. And here, what we did for now is just like returning the object color when there is an intersection. But what I want to do instead of that is computing the light at that point. So how much light is received at this specific point in space. So we will start with what we call direct lighting. So this is the light that is coming directly from all the lights. So to do that, I will, at this point, need to iterate through all the lights in the scene and make sure there is a direct path from the light to this point without intersecting with like any other objects. And that's all. Again, trusting CoPilot. So I just added like direct light property and the for loop, and then everything is generated. So it looped through all the lights, computing the light duration. Sorry, here. It's also generating a ray using my own convention. Recursively call the find intersection method, because basically what you need is making sure the ray from the intersection point to the light is not like intersecting with another object. And so it's calling itself the other function. And if there is no intersection, so no object is found between that point and the light, then adding that to the direct light. So again, this is pretty amazing, even if I don't know why this was here, like the distance is not a property of position, but except that lister mistake, everything was perfect. Also, the angle of light matters a little bit, so I will not go into details, but basically if the light hits a surface from the top, it will be more intense than if it hits it from here. So the angle of the light versus the surface matter. So we're just adding this. So I just type multiply vector because I knew that I need to multiply this vector. And again, CoPilot autocomplete everything. So that's great. Last step, I have to take into account the object color itself. So if I am, for example, a red light that is lighting a blue object, I don't want this blue object to be lighted because the light is only red. So I'm basically multiplying the final color, the direct light, by the color of the object itself, divide by 255 just to have like between 0 and 1. So this will make sure that the object color itself is taken into account. And that's all. So again, thanks to CoPilot, not a lot of code has been written. And now I have a scene with shadows, and I can see all the objects in the scene. So you can see we have this light here, which is actually considered to be what we call a point light. So here you can see the light is squared. But when I simulate the thing, maybe you've noticed it, like I'm only taking the position of the light, which is like a single point in space. And that's why like the shadow here, the shadows are very sharp. There is like no smooth things. It's very, very sharp because of that. And that's our next step, making sure like this light is not actually a point, but a square. And this will make things more real and the shadows a little bit smoother. And guess what? We'll use Monte Carlo for that. So let's Monte Carlo it. So now for the light position, we are taking only a single point. The idea is to move from the single point, and again, generate random points in a square for the light position to be able to simulate that. So instead of, for every moment we want to compute light, we will need to iterate through all the possible position on this light. We just like choose one point randomly on this light, And on average, this will act as a square light. So first step, instead of having a position for that light, I just added a simple function that is generating a point randomly on a square, the square that represents the light. So the value does not matter here, but that's what it does. And here, again, very simple, just made 2 updates. So I replaced the light position by the function call. So I stored it in light position and replaced it at the 2 places it was used. And that's all. And here we are. Now the shadows are not sharp anymore. This is very smooth, and this is acting as a light in a square shape. So now you can see, like, thanks to this framework and this like randomness and the fact that we are averaging the results every iteration, it is very, very easy to add new behavior that looks more real. And this is like only 100 paths per pixel. Okay, last step, indirect lighting. So this was direct illumination, but for more real cases, we also want indirect illumination. So the light at one specific point in space is not only the light that comes directly from lights, but also from other objects bouncing on the walls, for example, into the scene. So I would have expect from the sphere to be also lighted a little bit in green on the red because of the light coming from the light to the green wall to the sphere. And this is what we will try to do here. So on a specific point of space, the light can come to an hemisphere that is on top of this position. We can sample a ray from it and like launch a new ray from that to try to like get the color of indirect lighting. But if we do that uniformly, we will have to like multiply by a factor of the angle of the light. And this will mean we will lose a little bit of time and poorness of the Monte Carlo method. Because basically, if we are choosing a point like right here on the hemisphere, the weight of this point will be very low, like 0.1. And so we are like shooting a ray just for a 0.1 impact on the average, which is bad. So what we will do here, we'll use this cosine weighted hemisphere. So instead of like generating randomly a ray on an hemisphere, we are already like in the random generation, choosing arrays that are more probability to be on the top of the hemisphere than on the border. And so we don't have to multiply by any factor, and that means every ray we shoot will have the same impact on the final result, which is great. So we'll need less paths per pixel to have the same results. And here, CoPilot failed again, because again, same example, there is a lot of different ways to do it, and it failed to like take all the context to write the correct thing. So I just had to like fix it, and it could be like complicated to generate these rays into the hemisphere. But after that, Monte Carlo was able to follow. So generating for every ray that every time I hit basically an object, instead of going only to the lights and compute the direct lighting, I will also launch an indirect ray recursively to compute this indirect lighting. So here I'm just like generating the indirect ray. So the point of origin is the intersection point itself. And the direction is used by this indirect ray direction thing, which is using my cosine weighted hemisphere. And to compute the indirect color, again, like CoPilot at here, it's just like recursively call my function. And so you can notice def is now useful here. And we can do that like indefinitely. If you want to consider all the incoming light, you have to have an infinite depth, because the light can bounce like 10,000 times on objects before reaching another one. But of course, we will limit that. So I will add a depth limit, which is like 2 or 3 is often more than enough. So if it reaches that limit, I'm just returning black to make sure to like don't go infinitely in recursion. And at the end, I'm just adding the result of this indirect color for the other ray I shoot to the final results. There is a pi multiplicator here, but very complex to explain, but that's because of the shape of the hemisphere. And that's all. Ambient light it is. So you can see the results now is a lot more realistic because instead of taking only the direct light, we are taking indirect light. So you can see here the green because the light bounces on the wall. And even here on the shadow, the red from this wall. So this starts to be very realistic, and you can use that method to go a lot further. I have put you a link on this presentation that I will share to everyone. So basically, I would like, if you want to implement reflection, so I've shared my code here on this like CodePad link. You can like get the code and try to implement reflection. So basically, reflection is also very easy. Instead of shooting a ray for indirect light, you will shoot another ray, again, another one for the reflection. So you just have to compute the reflecting ray. And this can be very easy with CoPilot. And taking this into account to the final color. Now, I just want to ask you a question on the chat. So what is this number? Guesses? 80-20 rule, yeah, kind of. This is actually my level of honesty because yeah, this is like the 80-20 rule. Basically, I had a little bit to retro-engineer CoPilot to be able to do this talk in this order because sometimes it was failing, and it actually requires a lot of debugging and like finding the right function name until it generates a good solution. So I would say like 80% of the code and 80% of the time, CoPilot gave me the right answer right away. But for the 20% remaining, it was hard to debug and to like retro-engineer CoPilot to like pointing him in the right direction. And this is one of the reasons also I didn't do that talk live because it is like too random and sometimes it generates very, very weird thing. And so these are like my few 2 cents on CoPilot. I think to use that, you need like very good debugging skill because when someone goes wrong, it is very hard to debug because it's like not your own code. So you're taking a lot of time to understand the code. And basically sometimes it's just like easier to like remove it and start over. But it is very, very good for prototyping and like very simple unitary things. As you see, like the intersect with triangle, this was like a perfect example, very complex function, but very unitary. So this gave great results. It's also like best when the topic is mastered, like very as a co-pilot, but not at all to learn how to pilot because it's like it's too random and you will lose a lot of time trying to debug it. And it also fails often on functions that are too complex with too many different possible implementations, which are like very strongly linked to other chosen implementation and coding style on the other part. Also, like I didn't use like TypeScript, for example. I don't really know if that would have helped a little bit or no with the typing to like choose the right implementation for a function, maybe. So next step, very quickly, I just want to go through with you all the possibilities of ray tracing to maybe give you also the desire of implementing your own, because all the things I will show you are not that hard to implement one by itself and produces very, very nice results. So the first one is just about random sampling methods. Again, could talk like 1 hour about that, but there is a lot of different ways to generate random things. And depending on these methods, you can have like better or not results to like get the best out of randomness. Like for example, you can like generate randomly a point, but you can also do what we call jitter sampling. So like split a grid of like 5 by 5, and in each square of that grid generate a point. This is more like uniform, and so it will be like closer to reality with less samples. So that is something that could be implemented that is really nice. Of course, there is like transparency absorption, which is also not that hard to implement. So basically, you have to shoot another ray that will go through the object, and it can also take into account the like I don't know in English how to say it, but like depending on the material, the way the ray is going through the object. So it's like deforming the shape of the light through an object, or you can see like the nice results on my render here through the glasses and the ice. We can, maybe you've noticed here the beach in behind. We can also use a cube map. It is called Caustics. Yes and no. Caustics are the way the light is coming through and generate like very, I will go through it later. I actually have a slide for Caustics. So cube map is also very simple to implement. So the idea is like instead of when you're not hitting an object, just taking black, you're taking like a pixel from a picture, a cube that is basically around your scene. And this gives very nice results without having too many objects on the scene. So like here or here. So this is nice. Dispersion, spectral lighting. So also like in reality, in physics, when a light goes through an object, actually it's depend on the wavelength. The light can have a different path. And so this, you can see on my render here through the diamond, there is this like kind of rainbow distortion of light, dispersion of light, which is also kind of nice. And for that, you will need to get rid of RGB representation and use wavelengths, which can be tricky, but also not that hard and produce nice results. BRDFs, so that's just like fancy word to say like the way we are sampling how the light is bouncing on an object can be modeled by this like BRDF functions. And this give also great results to like model a lot of different materials and different way the light will bounce on these materials. If you want more triangles, we will need also to be fast, better representation. So we use also Octrees. So it's just like ways to split the scene in small parts. And instead of going through the million of triangles of this dragon, for example, you will just like intersect with these boxes first. And only if it intersects, go through all the triangles. So this helps a lot to improve the performances with scenes and a lot of triangles. Because you have to go through the list of all objects if you want to make sure you intersect. Volumetric scattering, so also like you see like this nice dust effect here, the light. So also taking account that this volume can bounce light too. A little bit more complex to implement, but gave insane results. Caustics, here we go. So to be able to see caustics, it's actually very hard with path tracing because like the way we are generating randomly rays, we have very, very low probability to actually hit the light and bouncing through objects multiple times to go to the light. So what we usually do is use with path tracing photon mapping. So photon mapping is kind of the opposite. From the light, we are shooting rays and we're generating what you see on the left. It's a photon map of all the photons that like go from the light to anywhere on the scene. So you can see here and here. And we are adding that to the path tracing method to generate here this nice caustic. And of course, you can take the poorness of parallelization because it's very, very independent. Like for every ray you shoot, you can use threads, you can use your GPU, you can use network, everything you want to be able to compute that. And everything, the only thing you need is basically the scene and the coordinates of your ray. That's all.
Hey everyone, Mathis here. I just wanted to let you know that the video you just watched is part of a series of conferences we host at Coding Game. It's monthly, it's online, it's free. So if you want to register for the next session, feel free to do so. I'll leave a link in the description. See ya!